Good morning or good afternoon or good evening, depending on where you are on planet Earth today. Today, we are uh, delighted that an old colleague of mine, Paul Gazis, is going to talk to us about some really, I would call ancient data sets, at least in the space science realm, on Pioneer 10, 11, and Pioneer Venus plasma analyzer spectral data sets. So, Paul, why don't you share your screen and tell us all about them? And please mute if you're not speaking otherwise.
Okay, I'm sharing my screen now. Let's see if this works. Screen. Okay, can everyone see my screen?
Not yet for me.
Okay, let's try this again. So it was an adventure. Share screen, screen, share. Okay, now have you got it?
Yes,
Yeah.
that's better. Yeah.
Okay, slideshow. Here we go. Okay, my name is Paul Gazis. I joined the plasma physics group at NASA Ames Research Center back in 1983 and remained with it until the end. Um, During that time, in addition to doing my ordinary research, I also oversaw the data production for the plasma analyzers on board Pioneer 10, Pioneer 11, and Pioneer Venus. And I'm going to be talking about the spectral data set from these instruments today. Um, Pioneer 10, Pioneer 11, and Pioneer Venus were launched, early in the middle, towards the end of the last century. They returned spectra of solar wind and magnetospheric plasmas between 0.72 and 63 AU for more than two solar cycles. Data from these spacecraft from the plasma analyzers were generated and maintained by the Space Physics Group at NASA Ames, but due to the very profound limitations and resources at the end of the mission, we never had a chance to distribute all of the data to the space science community on a large scale. The spectral data set from these spacecraft is potentially incredibly useful. You can use it to look at a variety of physical processes in the solar wind, the magnetosphere, and various near Venus, Jupiter, and Saturn. So I'm going to talk about the missions, the experiments, the data, things you can do with the data, and how I am hoping to make it available to the community at large. Pioneer 10 was launched in 1972 in March, back when I was in high school. It encountered Jupiter in December of 73 when I was a sophomore at Caltech. It became the first spacecraft to leave the solar system when it passed beyond the orbit of Neptune in June 1983, around the time I got to Ames. Pioneer 11 was launched a year later in 1973, encountered Jupiter in 1974, Saturn in 1979, and here's a plot of the trajectories of the spacecraft themselves. The top panel shows Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2 trajectories in the ecliptic plane with the direction of the incoming interstellar medium. The bottom panel shows heliographic latitudes of these four spacecraft. Pioneer 10 was the first, and it remains the only spacecraft to head downstream with respect to the incoming interstellar medium. And unless something changes dramatically, it might be the only spacecraft to explore that region of the heliosphere during our lifetimes and possibly during this century. Um, Pioneer 11, well, it went in pretty much the same direction as Voyager 1 and Voyager 2, explored a time region that these spacecraft didn't explore. It went upstream with respect to the LISM one solar cycle earlier. And it was also the first spacecraft to return any outer heliocentric data from significantly above the solar equator. Here are some mission milestones. The important thing for the purpose of this talk is the last plasma data from these experiments. At Pioneer 10, the power source degenerated to the point where we could no longer run our instrument in March 1997, when September of 1995, when the spacecraft was 63 AU from the sun. Mission formally ended in 97. The last useful telemetry was in 2002. I suspect they probably still had data from the Gamma Ray Telescope at that point. And the last signal was in 2003. Pioneer 11, the power source for that spacecraft wasn't quite as robust, so we ran out of power to run the plasma analyzer in April of 1992. And the spacecraft itself ran out of power in 1995. Pioneer Venus was launched in May of 1978, entered orbit around in Venus of December of 1978, and it then returned data for almost 14 years. We ran the spacecraft until we ran out of power, fuel, and altitude in October of 1992, and they actually did a more or less controlled reentry, receiving data all the way down as the spacecraft entered the atmosphere. The instruments on these spacecraft were conventional quadrispherical plasma analyzers. On Pioneer 10 and 11, we had an energy range of 0.1 to 18 keV. The Pioneer 10 and 11 instruments consisted of two detectors, Detector A and Detector B. These were oriented parallel to the spacecraft's spin axis. They swept out a cone of phase space pointed towards the Earth, which meant that for most of the mission, they were also pointed directly at the sun. Detector A used 26 channeltrons. Detector B employed 5 targets that measured current directly. And the instruments operated in a bewildering variety of scan modes, instrument modes, and sampling rates for protons and electron data. The Pioneer Venus plasma analyzer was a duplicate of the detector A's on Pioneer 10 and 11. Unlike those, it was oriented perpendicular to the spacecraft's spin axis, and it swept through a cylinder of space paste that sampled both the incident solar wind and the Venusian magnetospheres. I can actually show you where these instruments were. On Pioneer 10 and 11, our instrument was tucked away behind the high gain antenna, right around here, between the high gain antenna and the magnetometer boom. On Pioneer Venus, I believe this was our instrument. So every time the spacecraft rotated, it swept at a nice swath of phase space that included the incident solar wind and anything that might have been coming up towards the spacecraft from Venus. Here are the instrument parameters. It's a chart that I concluded mainly so you can look at it after the talk is over. The important thing here is the difference between Detector A and Detector B. Detector A had 26 channeltrons. They had a resolution and angle of 3 degrees for the central channeltrons and 8 degrees for the channeltrons on the right and the left. Detector B had 5 targets. Since they were covering the same amount of angle, they had much less angular resolution, 15 degrees for the center 3 targets, 47 degrees for the outer targets. And Pioneer Venus was a duplicate of Pioneer 10 and 11 Detector B. Detector A was more sensitive. It's sensitivity dependent on the gain factor. I'll talk about that briefly later. Detector B, the bottom line is we could get down to densities of about 0.001 protons per cubic centimeter, and we could go up to as high as you wanted, really. So we could detect solar wind out to 60 AU, really. The plasma analyzer data production was had quite a long and checkered history. The raw data was delivered to us on EDR tapes, originally 7-track tapes, later 9-track tapes. We calculated the plasma parameters directly from the tapes using least squares analysis. And due to limitations of the earliest computers, for the first few years of the mission, we could only calculate 1 fit per hour. So it was fits done in a CDC 7600. Those of you curious can look up its specifications, and you'll be astonished at just how incapable a computer it was compared to modern electronics. During the first years of the mission, before I got to Ames, they made no effort to save the Spectra themselves. In 1983, realizing that the Spectra were in danger of getting lost forever, pretty much at my instigation, we began an effort to extract the raw spectrum of all our old tapes and record them in the original instrument counts. And this spectral data set was saved in a dedicated archive. We developed algorithms to convert the spectrum instrument counts to actual physical units, account for aberration, the effective instrument response function, and do moment analysis to give us an alternate way of calculating plasma parameters. And those moments analyses are what we use to get parameters for the last 5 years of the mission. The spectral data set, it's 6 gigabytes worth of data in 209 files. There's somewhere between 200,000 and 300,000 spectra. I've never counted them. And there's a large collection of metadata to go with this. Originally, we saved these all on a room full of 9-track tapes. As technology aged, we moved them through a succession of media, in one case, narrowly escaping destruction. as drives ceased to function around the time before we could replace them with a different technology. The data is now preserved in multiple copies and on different independent media, and on several different computers that I maintain myself. Each spectra is recorded in a special ASCII format that I'll show in the next slide. The metadata include documentations, descriptions of the data format, ways to convert from instrument parameters to physical parameters, a record of the instrument response function, and source code for working with the spectra, along with several boxes of physical documents. Here is what the actual spectra looked like, and I should expect some muted laughter at this point as you look at this slide. The left side here shows an actual record of one spectrum in the format that we eventually decided on. Each record consists of a header block, which has the spacecraft name, detector, instrument mode, high energy ion or electron mode, a time stamp, various instrument parameters, followed by a data block for the maximum flux mode energy instrument mode. Each data block consists of a succession of lines, which give you the energy step, the sector number, which is spacecraft roll angle, and signal from the 5 targets and instrument counts. Now, looking at this, you'll conclude that it's almost unreadable by anybody who doesn't know exactly what its contents are. And this is just the way we had to work back in the 1980s. Due to the very severe limitations of data storage back then, we had to sacrifice clarity in favor of economy. There was no other way we could save all the data. Back then, 1 gigabyte was considered enormous. Nowadays, I don't think we can even buy USB sticks that small. Even so, even in its original raw format, you can still work with it. Here's what the previous spectra looks like if you plot the instrument counts versus energy step for target 3. And you can easily see the solar wind peak here. You can see that it was centered around energy step 27, which works out to about 400 kilometers a second. You can get a rough idea what its width is, from which you could calculate temperature. You can count the number of the signal underneath the area of this thing. That gives you density. And we have a large collection of documentation and tools for working with these spectra. We can port these tools to modern languages, and I've already begun this. That's why I made this figure. But I'll be the first to admit that the raw data are not easy to use. So what we want to do is reformat them or reprocess them to make them more readable.
Sorry, Paul, can I interrupt for a second? Is it possible that some of the width of that profile is simply instrumental, or are you confident that we're resolving the?
Yeah, there's some of it is, but it's not for this particular spectrum. It's no big deal, and you can compensate for that. So that's what happens when you start compensating for the instrument response function. I know how to take the effects of instrument resolution out. Anytime I refer to the instrument response function, it's exactly that, how you deal with the resolution limits in energy when we're measuring these spectra.
Got it. But each of the points or steps, there's like a half a dozen points here. Each of those is a discrete energy channel that you.
Yeah, each of these is an energy channel, and these energy channels are about 17% of the energy wide. So if you have something like 30 or 40 steps, you're resolving with the spectra is much bigger than the resolution of the individual energy steps. Once you get down to 3 or 4 energy steps wide, you start having to deconvolve the width of the energy steps to get a rough idea what the actual spectra looks like. But this is something that we figured out how to do back towards the end of the mission.
Okay, great, thanks.
Yeah. So the question at this point becomes, what can you do with these spectra? What are they good for? And the immediate answer is we never had a chance to find out. There were only 3 of us in the project towards the end of the mission, and we had our hands full doing other things. The only published study that we did using these spectra was a survey of interstellar pickup ions that the late John Mihailov did back in 1998, and some design work that we did for a study of alpha particle enhancements after the LMAL workshops that I never had a chance to finish. But the potential uses of these spectra are quite enormous. I'll start talking about a few of them. The first, my favorite, would be a study of alpha particle enhancements. It's easy to detect the alpha particles, and they show up as a separate peak that's about 5 energy steps to the right of the proton peak. And as I say, we never had a chance to look at them. I started working on analysis code for this, and then I had to drop the project because I just didn't have time. And measuring the alpha to proton ratio is very simple. All you need to do is compare the areas underneath the curve. So you don't need to know anything about the instant response function or resolution. You can get the alpha particle to proton ratio, density ratio directly just by measuring the moments without accounting for anything else. It rather surprised me when I did the calculation and realized this. Another obvious thing to do with the spectra is look at shock crossings. Early in the mission, the spectra are taken about 10 minutes apart, which is enough to, it's not as good a resolution as the magnetometers, but we can still resolve the shocks quite easily. And sometimes the spectra even will span the shock crossing itself. Here's an example of a crossing of a coronal mass ejection shock. It was seen at Pioneer 10 in day 73 of 1973. We had one spec that was taken before. Here was a spectra taken before the shock. You can clearly see the proton peak, the alphas, some noise. Here's the spectra taken after the shock. You can see the proton peak's been displaced something like 8 energy steps to the right. The solar wind velocity has gone up from 380 to around 800 kilometers a second. The spectra after the shock's a lot wider because the solar wind has been heated. And there's a lot going on here that would be interesting to look at. And one spectra actually was taken during the shock crossing itself. So the low energy step part of the spectrum was taken before the shock, and the high energy part of the spectrum was taken afterwards. And I'm sure we could learn something from these. I just haven't had a chance to figure out what it was. Another thing you can do with the spectra is you can look for deviations from isotropy. It's pretty easiest to detect skewness. In this spectra here, taken after the shock, you saw on the previous page, it's pretty easy to see that there's a high energy tail here that's swamping the alpha particle peak. So skewness you can find by looking at the spectra directly. Other deviations from isotropy, like oblateness, you can measure directly using some of the instrument modes, and you can infer them with spectra taken from the other instrument modes. But this is someone nobody ever had a chance to look at. There's a lot of physics here, but nobody has really had a chance to look into it. Pioneer Venus pickup ions, these have been studied directly. There were studies taken during the early stage of the mission, but because computers weren't very good back then, the studies all had to be done by eye. People had to look at all the individual spectra one by one, one after another, look for peaks that might correspond to pickup ions and keep track that way. And because this had to be done by hand, because they were limited to regions where investigators expected to see pickup ions. Nobody ever did a large-scale survey. Nobody's ever looked for pickup ions or other phenomena in places where we don't expect to see them. There's a list of other things you could do. You could look at how spectra change during current sheet crossings, and there's got to be some information you could get looking at slow energy particle events, cosmic ray enhancements, could affect the spectra somehow, wave-particle interactions. It's got to be something going on there. No one's ever looked at the electron data. When I got to Ames, people just dismissed it, said it wasn't any good. I had no idea why. Nobody ever told me. Interstellar pickup ions can be detected using detector A in Pioneer 10 and 11. In principle, you could look for them with detector B, but this has never been done. And the thing I would like to do is reprocess all the spectra from the first years of the mission to generate high-resolution plasma parameters rather than just 1 point per hour. And finally, it's the question of serendipity. As I say, the spectra has just been sitting there. Nobody's looked at them. I suspect that the most valuable potential applications might never have been identified. We're never going to know, unless you preserve the data, what those applications might be. So now we get to the meat of the issue, using the data. In their current form, the Spectral data set requires specialized knowledge to interpret. There's only a few people left who know how to read it. It's all well and good, but who has the time to dig through all the old notes and figure out what they mean? What I want to do is put together software and documentation to convert Pioneer 10, Pioneer 11, and Pioneer Venus spectra to a form that everybody can use. And most of the software before this was developed during the final years of the mission. It was just never run. I've begun reviewing all that material. I've begun porting the code to modern languages and putting it into production. And I've begun figuring out ways to turn the Spectra into more readable form. But this effort's only begun. The goals are, I want to ensure that the current data set and supporting documentation are preserved somewhere. I want to convert the Detector B and Pioneer Venus orbiter data to a form that's easier for people to read, understand, and use. I want to find collaborators who want to use this data and work with them to make sure that the data are, in fact, easy to read, understand, and use. Once I'm happy with it, I want to deliver it to results to the appropriate archives. Along the way, I'd also like to deliver some even older data from Pioneer 6, 7, 8, and 9 that we found lying around in the later stage of the mission, but never had a chance to archive. I want to do a feasibility study to figure out what would be required to use data from Detector A and Pioneer 10 and 11. But the key to all of this is finding people who want to use the data to make sure that it's usable. It would be very easy for me to reformat the data, deliver it to the SDC, and maybe 20 years later, someone would look at it and go, I don't know how to read this, and it would be gone forever. Now, there's several levels of data restoration I can do. The lowest level is just the data in its current form, raw instrument counts in this almost unreadable format. A higher level of restoration would be to record physical units in some self-documenting format like CDF, XML, or both. An even higher level of restoration would be to spectra and physical units with the correction done for aberration in the spacecraft attitude. And the highest level would be to correct for aberration, spacecraft attitude, and deconvolve the effects of the instrument response function and the limited resolution of the instrument. Software for all of these has been developed. I used it in the late 1990s to calculate calculate instrument, plasma parameters that are delivered to an SDC. But it was designed for moments analysis, and it's going to take a bit of fiddling to get it to write spectra themselves instead of plasma parameters. There aren't really many issues involved with using the data. As I say, all the raw data exists. It was used for analysis. The code to turn it into more readable form was written. The only real issues are accounting for spacecraft orientation at Pioneer 10 and 11 gets tricky early in the mission when the spacecraft could be pointing a large distance from the sun. It's easier late in the mission when the spacecraft will always be pointing at the sun. There's noise in the outer targets for targets 1 and 5 for Pioneer 10 and 11 Detector B, which has to be characterized. Roll angle information for Pioneer 11 was lost. For some reason, it wasn't transferred during one of the transfers from one form of media to the other. You can work around this. You can infer roll angle information from magnetometer data, but that's just the reality we have to deal with. The data volumes are pretty modest. Right now there's only 6 gigabytes worth of data. Even if I convert it to XML, I doubt it would be more than about 32 gigabytes worth of data. So there shouldn't be any storage problems there. Detector A is, however, an issue. To use that data, you need to know more things, and I'm going to discuss this in the next slide. Detector A is really the best detector in all these spacecraft. It has greater sensitivity and angular resolution than Detector B. You can use it to detect the interstellar pickup ions. But to do this, you need to understand the detector gain factors. And these were recorded in a series of notebooks in the latter part of the mission. It's going to take some work to read them, turn them into numbers, and figure out how to use them. I think at this stage, all I can really do is review the notebooks and put together a feasibility study to figure out what would be required to use the Detector A data. Another thing we have lying around, we're on the subject of old data. As I said, during the final stages of the mission, we discovered that we had what seemed to be the only remaining copies of plasma data for parameters 6, 7, 8, and 9. Most of this has been delivered to the NSSDC, but I just don't think they have all of our spacecraft. So if anybody, it's going to get delivered, but well, this is happening. If somebody wants to look at it, I've got it. So summarize this presentation. In my opinion, the spectral data set from the plasma analyzers on Pioneer 10, 11, and Pioneer Venus has considerable value. I've been preserving it from the end of the mission, but as the number of people who know how to read it dwindles, the data set's in danger of getting lost forever. I've begun an effort to convert it to a more usable form. I'm going to put together a data restoration proposal to finish this task and deliver them to the appropriate archives. But for this data restoration effort to fly, I really need to find other users now to read the data and ensure that it in fact is readable and can be used for something, and also to do some science. So that's it. That's presentation, and I'm very much open to questions.
Okay, great. Thank you so much, Paul. That was really wonderful. I see that Glenn has his hands up. So if you want to ask a question, please raise your hand and I'll call on you. Go ahead, Glenn. Thanks for dialing in.
Well, I just want to say this would be incredibly exciting as somebody I've looked through all of the the Pioneer Venus orbiter data that I can, and I've looked through all the Venus Express data. Please count me in, as I'm sure there'll be a lot of people who will say they'd be fascinated to really dig into this PVO data set. I think incredibly valuable. So we could, do it, especially given the limitations of the Venus Express data set. Right, and I'm sure there'll be things here. I think that would be fantastic. Please reach out to me. And I see Futana-san, who has his hand up as well. So great. But yeah, this would be very, very exciting.
I think anybody who wants data, send me email. I'm going to start putting together a directory and a whole new project to get the data out to people. So send me email directly. It's going to be far easier for you to remember one of me than me to reliably remember all of you. And I can deliver the Pioneer Venus data set in its current format immediately, and we can start working with figuring out how to enable you to read it. Yeah, but definitely, but yeah, I'd be happy to get out to people. Just get me emails and I'll start figuring out how to do this.
Okay, Futana-san,
Okay,
you had a question.
Yes, thank you very much. Really, really exciting talk. And then, nice to meet you. I'm Fujana from Swedish Institute of Space Physics, and I'm PI of an Aspera 4 instrument of the Venus Express. And as also Green said, but it's quite a great collaboration. I mean, just I realized that a lot of data analysis together, it should be done together with Aspera 4 and then this Pioneer Venus orbiter data. I mean, we always refer to the Pioneer Venus orbiter data for example, an escape rate study, but sort of raw data is sort of difficult to be accessed. So it's really, really a good initiative. So I think we need some joint activity between Aspera 4, Venus Express, and the PVO, and definitely it's a great opportunity. Yeah. So just want to say thank you first, and then we started this collaboration, I think.
I'll make sure to connect you all up together. No problem there.
Yeah, and I would really like to see some science done with this. I'd be happy to get involved in any projects, but the first step is to get the data to people in readable form.
Yes, that's of course a difficult side. I mean, for us also, data processing is quite well, let's say headache. It's a time consuming, but yeah, I mean, it's a lot of new science also popped up for Venus Express. And we tried somehow to go back to the PVO data as well before, but we couldn't find good data source. So it's a lot of ideas, so say, and new sort of findings which can be seen on the Pioneer Venus orbit as well or not. That's probably the start point. But yeah, I agree that the data, mutual access of data, that's the first step.
Yeah, we delivered the spectral data for Pioneer Venus, Pioneer 10 and 11 to the PDS some time ago, but when I look through their data holdings, some of this seems to have vanished without a trace. That's another reason why I would like to get some collaborators involved in this, get more usage, and make sure that the next delivery to the PDS doesn't get lost and is readable by everybody.
Great. Go ahead,
And what
Jan.
happens is you deliver it. Go on.
Jan, we can't hear you.
Okay, hi, Jan here. Jan Bergman at the Swedish Institute of Space Physics in Uppsala. And I fully agree with Fritana in Kiruna. So this is extremely important that we gather the data and make it usable for future generations, as you have done here. And I would say that even now, with working with the U spacecraft, we have some difficulties to align the housekeeping data. I mean, like the attitudes and so on the spacecraft, and where we were measuring. So this is a great effort. Thank you so very much for your talk.
Yeah, and I see that Gwen mentioned maybe putting together a list, email list or something. I'll try to do that. So anybody can email
Great,
me.
yeah.
I can add your name to that list. And again, Paul, I'll put you in contact with the people that have asked the questions today.
Okay, thanks.
Yeah, and what I do, I think we talked about, you and I had talked about this earlier, sometime in the very near future, I'll see about getting the raw data up on the cloud somehow in its current form, just so people can grab it.
Absolutely.
Maybe not tomorrow, but sometime in the next few weeks. And we can go from there.
So I one more thing. So what I've seen from payload providers, that they are keen to provide payloads, but then when the mission is launched and the data is coming, we have problems to get funding from our space agency to actually work hard to keep this valuable asset from the spacecraft down to ground and make it usable for everybody. So thank you very much.
Yeah, that's always been a problem. This particular data set has been slipping through the cracks for the better part of 2 decades. We'll put a proposal for restoration in one particular project, and the project will say, this is great, somebody else should fund it, and this has gone on and on and on. And yeah.
Okay, Jeff,
time
go
to
ahead.
fish or cut bait, make sure it does get saved.
Good work. Thanks.
Go ahead, Jeff.
Yeah, I just had sort of a comment. Paul, I'm a little surprised that you emphasize the difficulty of reading the data. The one example where you showed an ASCII file, to me that was perfectly legible, and once you understand the meaning of a half a dozen columns, you have it. So, and if that same data were put into a FITS file, to me it would be much less readable. But the practical question I have, though, is I think more of a limit might be calibration. You didn't mention too much about, was there a pre-flight calibration of the energy determination?
That's what I meant about the energy, the count to energy conversion. There are lookup tables that do just this, and
those are all
back up a bit. Yeah, notice here I didn't convert the energy steps, but I did convert from instrument counts to currents. This is actual currents. This is actual flux, and this was calibrated. This is well understood, and the conversion from energy step to actual voltage is also well understood. There are tables to do this, and that's where things get complicated. So there's 2 issues. One is that this is the simplest mode, the maximum flux mode. There are other modes. Full scan mode gets fairly complicated, since the data block has not just one record, but several records from taken pointed to different directions. Pioneer Venus is a bit more complicated because instead of there's each spectrum is taken in 3 different modes, and Pioneer, when you get to detector A, just forget it. But so there's it's a little bit complicated just reading this, doing the conversion from instrument counts here to actual currents is a little bit complicated. Going from energy step to voltage is complicated. They're just all these steps, one after another, which just get harder and harder and harder. And that's why, getting back to here, excuse me, I identified 4 levels of readability. The first is the raw spectra. The second is we do all the lookup tables and calibration to turn from instrument counts to physical units. Then the next step would be to correct for aberrations, since you do have to correct for that. If the spacecraft is moving away from the sun at 10 kilometers a second, and it measures an incident velocity of 400 kilometers a second. The real incident velocity was 410, and the spacecraft velocity can be high enough that you do have to account for it. And then finally, you want to account for the resolution issues, the incident response function and whatnot. And the way I would see doing this would be first, get the raw data online so people can at least look at it. Second, at my end, do the conversion from instrument counts to physical units, get those data sets up in CDF, XML, or FITS, and or all 3, and let people work with those, along with documentation for how I did this, so people could assure themselves I did it right. And the next step would be to correct for aberration in spacecraft attitude, and the final would be to do the incident response function. So the first step would be to get the raw spectra online and just let people read it and work with it and look at it, see what questions they have. I tell people I was doing that. I think the first thing I would do would probably put together XML, just because it's self-documenting, easy to read, but come up with a spectra and physical units in some self-documenting form. And what form I chose would be based on what people are most happy reading. If everybody says I want it in FITS, I'll do it in FITS. If everybody says they want an XML, the first step would be to do an XML.
Or what about plain ASCII? But anyway, thanks, Paul. I got to go to another meeting, but thanks. This looks like really good stuff. And there's a lot of interest, of course, in particle acceleration in other parts of the universe, and I bet a lot of this data might be relevant to shock acceleration of particles.
That's the solar data particle event. Exactly. You'd expect to see the spectra change when acceleration is happening, and nobody's looked at it. I mean, there have been any number of simulations, a lot of electron particle interaction, of anything you could think of. But nobody's really looked at the spectra themselves. They've never had time.
Well, I forget, what's the Mach number and the shocks, roughly?
The
Mach number.
It's let's see. It varies. We're getting the full factor of 4 density increase, so it's pretty high.
Okay.
Shock velocities are in the 100 kilometer per second range. That can be it's high. It's very high.
Okay.
These are actually it runs a whole range. You get everything from shocks you can barely detect that are piffling along at about 10 kilometers a second to enormous events associated with CMEs that go cruising along at well over 100 kilometers a second. So and there's particle acceleration happening associated with a lot of these. And again, you can see something's going on. You can see the energy, the distribution skewed here, but nobody's ever said, what should I expect to see, and looked at the spectra to confirm that they're seeing it.
Right. Okay. Thanks, Paul. I gotta go. So.
Yeah. Okay, Glenn, go ahead. You're muted.
Sure. I said this in the chat, and I can't promise anything, but it just occurred to me that NASA Goddard, we actually have a lot of this data, PVO data, archived and under the Space Physics Data Facility, and I can't. And it seems like my personal opinion would be NASA should be stepping up here and looking after its own data. And this isn't Goddard's an obvious home for this. And I have I've got colleagues, Bobby Candy, a bunch of folks who work at SPIDF. It's possible if when we write a PDART that we could try and use support from. It would be cool if we could get support from them. I don't know. I can't commit them, but see if we could get support from them to help, be the interface, and you can try and format your data so we can all get it up into into SPIDF. It would be fantastic to see this data
We should.
in its home.
I was putting together a PDART for half a year effort to get started on this. We should coordinate because the way I see it, as I say, I have considerable experience with seeing this thing slip through the cracks because I didn't have a constituency. The more people who get on board, the more likely it is that this will fly. And I get increasingly antsy. It occurs to me I may well be the last person left alive who really understands how this is organized. And
I think
I'm not as young as I used to be.
Yeah, I mean, we could
really
also
want to pass this on to other people.
Yeah, we could get. There are people at Goddard who could probably help with. I mean, they would need funding, but that's what the PDART's for, right? But we could get them funding to be the people to catch. If we could get them in some format. Normally, what we can say, normally because mission teams do the data and do all that stuff, but it's like the mission team is just you, right? So we need. I can try and work with them and say, hey, Paul needs support. Like with this, it's like he knows his instrument, but I tried to make CDF and they're really complicated. So help with the interface. We have expertise here at Goddard. We're not asking for a favor. We want to write a proposal. We'll pay them, but that would be the idea. We put somebody on your team, on the payroll whose job it is to catch.
Yeah, my original thought was at least have people on the team who are going to use the data listed as unfunded co-Is or collaborators, but this would be even better. The bigger the team and the more coherent it is, the better. So let's exchange email and start figuring out what to do. Because if once the team grows over a certain, let's talk. We should talk offline.
I'll make sure
I have plenty of ideas. All of my planning was based into the assumption that it would be only me, and that I was trying to solicit other users to use the data to check my homework assignment, as it were. But if we bring more people on board, the possibilities change. We could do something more substantial.
Yeah, I think it's a really good initiative, and then definitely we in the Venus Express team can help, for example, in drafting some potential science cases for proposal. I mean, sort of in long term, say over 30 years, and 1978 to 2015, 14 in the gap in between, but still it's a long-term variations, different solar cycles. So it's quite, I think, complementary data. So I think for the proposal, for example, then we can help somehow. I mean, no funding needed. That's a good thing.
The 1986 solar was unique because the solar magnetic equator was just so well behaved. It was so flat. There's this there are a whole bunch of studies I did back in the late 80s that took advantage of this. So it's a time period that's worthy of interest in its own right.
Okay, go ahead, Mike Cheffin.
I just wanted to say that at last, we've recently had some success getting PDART funding to archive the Pioneer Venus Orbiter ultraviolet dataset and the Mariner 6 and 7 UV dataset, which were in a similar state of predating the PDS and therefore not having been archived at the time that they were gathered. I'm pretty sure, well, I can speak for myself. I'd be happy to share the proposal that we used to secure that funding.
Definitely. That would be of enormous benefit to me. I have a draft together, but I reached the stare at it and scratch your head phase. And then
if you're
scratching it, oh boy, that would be enormous help.
Yeah, happy to. If you're proposing to PDART, the restriction is that you can't do any science. You can only enable science. But with SSW, right, you could build an archiving effort into an SSW proposal or a discovery data analysis proposal that would do science and then also archive this data.
Yeah, my thought was PDART and see if I could get somebody else to be a co-I, and their function as co-I would be to verify readability. If they did science, happened to do science with it, that would be outside the proposal. So and so would be reading it, making sure it was okay, and any science they would do it would not be mentioned here. But I mean, I really do need. I mean, you've seen the issues. You really do need other people to try to read your product to make sure that it is readable. Otherwise, it's just going to be another unreadable set of files that nobody looks at. And the more complicated the instrument, the more serious an issue this becomes. See, I very much like to see the proposal you have, and yes, I'm aware that the thing shouldn't be doing any science, and that was not the proposal itself wasn't going to include any science. It was just going to be your archiving.
Yep, happy to help.
Great. Yeah, I'll make sure to connect everybody.
Great. Thanks, Mike.
Okay, any other questions for Paul? I think everything that was in the chat was basically put up in the question and answer. So okay, well, I think
And
you
I'll
all
send you. I'll get you a copy of this so you can distribute it to everybody. I'll
Yeah.
email you a copy as soon as the meeting's over.
Excellent. Excellent. Yeah, and I think you all have Paul's email, but regardless, I'll put people in touch with each other since I have all your emails, since I did reach out to you all. And really great. Yeah, and I think for one thing, for example, is data format. It'd be nice to just to know what PDS prefers or what people think would be the best for this complicated data.
I think what people think should override what they prefer. I mean,
Yes.
what people think is what people are going to use.
Yes.
And I'd be prepared to defend that in the proposal. And of course, there's no rule in the world that says you can't do two formats.
Yes, of course, exactly. Well, you said that XML and CD.
Yeah, that's exactly what I'm happy. I've spent a good part of the past 30 years switching between formats. Heck, I've been doing it ever since 1983. It is one of the things I do.
Okay, any other last questions? Okay, otherwise, thank you all for dialing in and listening to Paul and participating, and we'll be in touch. Thank you again, Paul. Excellent.
Okay.